using some trigonometric function. There we have learned that least square method, least square method basically deals with the minimization of square of the error. Minimization of the square of the error. So here basically we are trying to find list of that square of the error. So how we are doing? We are basically making that square of the error, and then we are taking the derivative of the square of the error, and then we are making it 0. That is basically similar to our minimization problem. So here first we try to find the error. As you can see, we will find the error. Okay, once we are able to find the error, we will take that square of the error, and then we will try to find the error with respect to unknown coefficient. Still we don't know what are the coefficient is. So while solving some problem, we'll see what is the coefficient. So if you take that derivative of the square of the error, if we make it 0, we'll get the equation like this. Okay. So now what happened? We can rewrite the equation in this form. So we're taking 2 right hand side. Okay. So this part will be 0. Now again you can see this is very similar to our weighted distributed method. That is our Galerkin weighted distributed method, where our weight function is the derivative of the error with respect to our unknown coefficient. In the Galerkin method, what we obtain our trial function as similar to our weight function. Our weight function is very similar, same as our trial function. Okay, but here our weight function is the first derivative of the error. In the Galerkin method, we obtain our weight function is same as our trial function. Okay, but here our weight function is the first derivative of the error with respect to some unknown coefficient. Okay, now we'll see how we can obtain that error and how we can take the derivative, how we can basically operate it. Okay, so once we obtain the first derivative of the error with respect to coefficient, okay, so we can do the integration like this. Weight, which is basically first derivative of the error, into the error that we are making 0 over the entire domain. Okay, over the entire domain in a average sense. Okay, the entire domain in a average sense. Okay, we are making the error 0 over the entire domain in a average sense. Okay, now here you just see what we are doing. We are assuming our trial function as a polynomial. Okay, so polynomial basically we can write as C0, C1x, C2x square, like that. We can assume some higher term. Okay, again we know the trial function also should satisfy the boundary conditions that our actual solution is satisfying. Okay, so for here, this is our simple supported beam. Obviously, our actual solution should satisfy that condition that y displacement is equal to 0, displacement y is equal to 0 at x equal to 0, and displacement y is equal to 0 at x is equal to L. So our trial function also should satisfy. Okay, so what actually we are doing here, we are satisfying that our displacement boundary conditions, okay, according to our physical problem. And once we do that, you observe that we are reducing number of unknown coefficient. Here you can see C0, C1, C2, 3 coefficient we have. So if you have 3 coefficient, obviously then our mathematical calculation will increase. So what we will do, we will satisfy our boundary conditions and try to minimize some coefficient here. So if you put u, which is our trial function, okay, that we assume as a plus bx plus cx square. Okay, so what we'll do, we'll put u is equal to 0 when x is equal to 0. Okay, if you do that, you will get a is equal to 0. Okay, one more time, what we'll do, by another boundary conditions, in the sense our displacement u is equal to 0 at x is equal to L. Okay, if you do that, what we will get, if we will do that, we will find that b is equal to minus CL. Okay, so this equation we'll find. Okay, b is equal to minus cl. Okay, now if you put the value, of a is equal to 0, b is equal to minus cl, and another option we have c. Okay, so now if you put that value in our in our originally assumed trial functions, okay, if we put this value in our original assumed trial function, we can find our trial function like this. Our trial function would be u, that will be c to x in bracket x minus l. Okay, now already we have discussed that we'll find the error and we'll take the derivative with respect to the unknown coefficient. Our now unknown coefficient is the c. We'll take the derivative of the error with respect to unknown coefficient, and then we'll try to integrate over the entire domain to make the error 0 in a average sense. Okay, so how we'll do? We'll put our trial value in our equations. We'll put our trial value into this equations. We'll put our trial value into this equation. Okay, so now here we'll have ei d2 u dx2. Okay, that value minus m0. Okay, that is not equal to 0. That is our actually error. Okay, now that is our actually error. Okay, so we'll see what the error is coming. So here we see that our error, basically our error is how much? U, we have to take the derivative of u is our c into x minus l. If you take the double derivative of this u, okay, if you take the double derivative of u, you will find that value of double derivative is basically coming as basically 2c. The double derivative will be coming as a value of 2c. Okay, so our error was ei dtu. Our error was dtu dx2. Okay, minus m0, that is our error. Okay, so this value is coming 2c, so our error is ei into 2c minus m0, that is our error. Okay, now what we'll do, we'll take the first derivative of the error and we'll assign at our weight function, and then what we'll do, we'll basically write weight function into the error into the dx over the domain. Okay, that is equal to our 0. Okay, now this is our error. So if you take the derivative of the error, d delta r by delta c, okay, because c is our coefficient. If you take the delta c, we'll get the value of delta r by delta c, that is our derivative of the error as a 2ei. Okay, now if you put the value of as a 2ei, that is our now weight, and this is our basically as the error, to the integration, and we make it a 0, we make that error 0 in average sense of the entire domain. Okay, you can find the value of c is equal to m0 by 2ei. Okay, now we already obtained our unknown value. Now here you can see our trial solution originally was c into x in bracket x minus l. Okay, and the value of c is your m0 2ei, m0 by 2ei. Okay, so this is our trial solution or approximate solution, and our actual solution is here. So here you can see for this particular problem, our approximate solution is coming same as our trial solution. So if you plot it, okay, you will obtain that this value basically overlapping with each other. Okay, if you find that, if you plot the value, you'll observe that these two values are overlapping with each other. Okay, so this is the basically least square method. Okay, and we have solved one trial functions. Okay, we assume one trial function as a polynomial functions, and we have solved one beam problem to see how basically we can find the error, how we can take the derivative of the error, how we can assign the derivative of the error as a weight function, and how we are making that error in the entire domain as a 0 in the as a average sense. Okay, in average sense, how we are making that error in the entire domain in average sense. We are making the error the entire domain. Okay, we are making the error 0 over the entire domain in average sense. We are making the error 0 over the entire domain in average sense. Okay, so this is the way we can solve some problem. Least square method. Least square method again is one type of weighted residual method. Okay, least square method is one type of weighted residual method. Okay, so I hope you get some idea. Thank you.